First thing, I want to make it clear that as in a lockdown period, I am not having any blackboard or whiteboard at home. That's why here I am explaining a solved example. Here we are going to analyze an indeterminate structure by using stiffness method. So if you observe the given beam, the KDA comes out to be 2. So unknowns will be, we are going to treat unknowns as theta b and theta c. Now let us take theta b equals to d1 and theta c equals to d2. Now the next step is the assigning coordinates. Assigning coordinates means we have to just assume the directions of d1 and d2. Remember, these are the just assumed directions. We don't know the actual directions. Just here in this example, we have assumed directions as clockwise. d1 and d2 here we have both assumed as clockwise. Next step is to draw a restrained structure. Drawing a restrained structure means just we have to make all the joints as a fixed joints. So here there are 3 joints, A, B and C. There are 3 joints. Just we have to make all the joints A, B, C as a fixed joint. Now next we have to apply load on it. Just we have applied load UDL of 12 kN per meter and a point load of 40 kN meter. As all the ends are fixed, so here we have find out the fixed end moments, and here I have shown the directions also. This is the calculation for the finding out fixed end moments. So already we know the formula for this. For UDL the formula is WL square by 12. For the point load the formula is WAB square upon L square. Here the applied point load is not at center, that's why we have used the formula WAB square upon L square and WBA square upon L square. Here just we have taken A and B as, we have taken 1 meter as A and 3 meter as B. Just we are going to put A as 1 meter and B as 3 meter. Now from this we have got the fixed end moments. Now the 2 diagrams are over, that is first is assigning coordinates and second is drawing a restrained structure. We have to show the moments along with its direction. First of all I have written here minus 16, minus I have written, that's why because up here the moment is going anti-clockwise, here the moment is going clockwise, that's why I written plus 16. Here it is moment is anti-clockwise, that's why I written minus. Here moment is clockwise, that's why I written plus. So I have written there AD1L, AD2L. What is that? Let us come to that part later. We'll go for the next diagram. Now how to draw this next diagram? Just here we have applied the unknown D1. Remember, the applied unknown D1 is going in a clockwise direction. We have assumed D1 direction as a clockwise. That means here D1 is applied at joint B. Just forcefully pick a joint B, and rotate it in a clockwise direction. We are going to forcefully pick a joint B and rotate it in a clockwise direction. Because of this rotation, this part is getting, that is member part AB is getting lifted up and BC is going down. Okay, just in red color I have shown a deflected shape, as A and D are fixed end, A and C are the fixed end. Here the slope will be equal to, at fixed end slope will be equal to 0. At fixed end slope is equal to 0. Here at B end we are going to apply rotation, and here I have done one tangent to that slope. So if I want to get theta equals to 1, I have to apply moment of this magnitude, that is 4 EI upon L. We have to apply a moment of 4 EI upon L. But remember, for AB portion, EI equals to 2 EI. EI equals to 2 EI. That's why I have taken here 4 into 2 EI upon L. L for span AB is 4 meter. So this is the moment 4 EI by L required to be applied at joint B to get theta equals to 1. Now to the next end, half of the moment will get carry over. Half of this will be just only EI. This moment is 2 EI, so half of it is going transfer to the next end with same sign. This is going clockwise, this is also going clockwise with half the of its magnitude. Now next come to the portion BC. So in the portion BC, again to get theta equals to 1, we have to apply a moment of 4 EI upon L. So again for span BC, span is 4 meter. So here to get theta equals to 1, we have applied this much moment, and to the next end half of the moment is getting transferred with the same sign. The applied moment is clockwise, so this will be also clockwise. Again, what is this K11, K21? Let us come to this part later. Here the whole diagram is to be multiplied by T1. Now this is the complete diagram for application of D1. Now come to the third diagram, that is application of D2. So D2 is nothing but theta C, and that is acting at joint C. We are assume direction of D2 as clockwise. Now to this restrained structure, we are going to apply a rotation, that is a unit rotation at joint C. So just forcefully pick this joint C, and rotate it in a clockwise direction. Forcefully pick this joint C and rotate it in a clockwise direction. Because of this rotation of joint C, this portion BC is only getting affected, that is this portion BC is getting lifted up. So to get theta equals to 1, we have to apply a moment of magnitude 4 EI upon L, and half of it moment will be transferred to the next joint, that is joint BC. Okay, so the magnitude of moment is half of it with same sign. This is going clockwise, this will be also clockwise, but half of this magnitude, half of it getting transferred. Remember, the most important thing is that here I have drawn this curve, at on the right side of this fixed joint. I have drawn this curve to right side of this joint because of application of this rotation, only the member BC is getting affected. That's why this moment is the moment MBC. So to show MBC, I have to show this moment in the BC region only. That's why on right side I have shown this curve. If I show this on left side, it means it is a moment BA, but here this span BA or span AB is not getting affected by this application of moment. Only the member BC is getting affected. That's why I have shown this curve on the right side of the joint B. This part is more important. Now this last diagram is over. Now to solve the given example by stiffness method, we have to form a stiffness matrix K, and we we have to generate these two simultaneous equations. So to get these equations we are required the stiffness matrix. We have to generate a stiffness matrix. Now come to the stiffness matrix. Now how to write the stiffness coefficients? So now come to this, the first diagram. So here we have applied D1, that diagram we are going to consider. Here I have written K11. The first stands for the position and second alphabet stands for the because of. What it means? So first of all I will explain the second alphabet, that is because of. So this total diagram is drawn because of application of D1. That's why the second alphabet here always will be 1, because this diagram is drawn because of application of 1. Now this is a B position. B for us it is a first position. Here we are taken a first unknown. Theta C is equal to D2, that is a second unknown, that is the second position. So this is the first position, that's why I written 1, and this total diagram is drawn because of application of first unknown, that is D1. That's why this will be K11. Okay, now at joint B, two moments are acting, this one and this one, and both moments are acting in a clockwise direction. So just we take addition of these two. This is 2A and this is only EA. Just we are taking addition of this. So this is K11. This is acting at joint B. Next, here I have written K21 because these two, that is these two means this is the first alphabet. First alphabet stands for the position. This is the second position. That's why I written here 2. And this total diagram is drawn because of 1. That's why I have written here 1. Now let us come to the last diagram. So in this diagram I have written here K12. So here the 1, that is the first alphabet, stands for the position. So this is a B position, that is the first position. That's why this will be 1, and this total diagram is drawn because of application of D2. That's why I written here 2. Of course this total diagram is drawn because of application of D2. That's why the second alphabet will be of course 2. Second alphabet will be equal to 2. This is a second position, that's why this will be 2. Remember I have shown here or here the first position stands for, first alphabet stands for position, second alphabet stands for because of. So this total diagram is drawn because of 2. That's why second alphabet always will be equals to 2. Here this diagram is drawn because of application of 1. That's why the second alphabet in this diagram will be always equals to 1. So here second alphabet is 1, second alphabet 1. Here second alphabet is 2, second alphabet is 2. Just first alphabet stands for the position. Here this is the first position, B is the first position. That's why first of all I here 1, here I written 1. C is the second position. So for this part, so here this is a 2, first alphabet is 2. Here also first alphabet is 2. So this way we can form a stiffness matrix. Remember, just we have taken the unknown as D1 and D2, and D1 and D2 are applied at joint B and joint C. That's why whatever moments acting at joint B and joint C, that is to be named with the stiffness coefficient, are given the names, that is are taken the K, right above K, at only the B and C position, are not given the any name to this moment because this is acting at joint A, and A joint is not a unknown joint. We have taken the unknown joints as B and C only. That's why don't put any stiffness coefficient to this joint, as the given beam is having KDA equals to 2, so it must form a 2 by 2 matrix. So here I have written a stiffness coefficient matrix. This is called a stiffness coefficient matrix. I have shown the stiffness coefficient matrix, so we are getting these values. Now come to the next part, drawing. So now consider joint B. Now consider joint B. At joint B, we will consider this equation: AD1L plus K11 D1 plus K12 D2 is equal to AD1. So now what is meant by AD1? AD1L means action in the direction of 1 due to loading. So now I will consider this restrained structure. This restrained structure, in this case we have considered a loading. Okay, so here I have shown a moment. These are the fixed end moments generated because of this loading. Now come to this B joint. At B joint we have considered D1 as unknown and assumed direction of D1 is clockwise. So we are taking here clockwise as positive. Okay, so here at joint B, 16 and 22.5 is the moment acting, but 16 is going clockwise, that's why we take it as positive, and this is going anti-clockwise, that's why we take it as a negative. So overall, because of loading, here there is L, that is because of loading, action means moment, action in the direction of 1 is nothing but joint B, action in the direction of 1 due to loading, we are getting this one. And now next, at joint C, that is the at the unknown D2 is applied clockwise, this moment is also clockwise, that means AD2L must be positive. Okay, action, that is the moment in the direction, D stands for direction, 2 stands for, that is second position, moment or action in the direction of 2 due to loading. This total diagram we are drawn because of loading, that's why AD2L is equals to this 22.5. I have taken this as positive because it is going clockwise. Now just put the values in this equation, we'll get one first equation. Now come to the joint C. Just here we are consider only joint B and C because only theta B and theta C is the unknown. That's why we are considering only joint B and joint C. And to joint B and joint C we are writing the two equations. So now come to the joint C. For joint C, consider this equation AD2L. Remember, C is a second joint. We are treated this as a second joint. That's why here we are considered AD2. So action in the direction of 2 due to loading. Okay. Of course, all these values we know. Just put these values over here. We are getting this second equation. Now next step is to just we have to solve this first and second equations simultaneously, and we are getting the answer of D1 and D2. We are getting the answer of D1 and D2. Just solve these two equations. So just solve these two equations simultaneously. Okay. Before going to the next part, so in this total example, the important thing is to find only the values of d1 and d2, that is theta b and theta c. Okay, so up till now we have solved the example in a technical way. So I have explained the total example in a technical way. So here I have used these two equations. These are two equations. Okay, now just if I consider that if one of the student is not knowing the stiffness matrix, how to use this k11, k12, how to write this coefficient, if I consider that the student is not knowing this thing, and if I consider that at the time of exam the student has forgotten the equation, if at the time of exam the student is forgotten this equation, now how to solve this example? Even if any student is not knowing how to write this stiffness coefficient, or if the student is not knowing how to write this equation, okay, even that student also can solve this example. Now how to solve the example in another way, I will explain that thing. Of course, to get values of d1 and d2 we are required two simultaneous equations. As there are two unknowns, to get two unknowns we are required two simultaneous equation. Now to get two equations, again we are required this k11, k12 like this, that is we are required stiffness coefficient. So instead of writing down this stiffness equation, still we can get these two equations. Now how to get these two equations, I will explain that thing. Now at a glance, see the total diagrams. We have drawn the total 3 diagrams. So how to write the simultaneous equation? To write the simultaneous equation, just come to the unknowns. So unknown is, first unknown is theta b. Theta b is adjoint b. So now to write that equation, just consider a joint b. So just I have drawn this a box. This is a blue box I have drawn. Okay, so just consider joint b only. So whatever is the moment acting at joint b, consider write that thing, means we will get a equation. Remember, so here I want to get this equation, that is this equation I want to get, that is first equation. First equation is related to theta b. So just whatever is the moment acting at joint b, writing out that thing means we are going to write this equation. So now come to this joint b. So at joint b the moment applied is 16 and minus 22.5. just take addition of this, we are getting minus 6.5, minus 6.5. Next at joint b we are getting this moment, that is 3ei plus 3a. So plus 3ei, write down this plus 3a. This total diagram is multiplied by d1, that's why I am multiplied by d1. Now come to joint this b. At joint b moment applied is ei upon 2, that is 0.5 ei. Again this total diagram is multiplied by d2, that's why it is to be multiplied by d2. Now next it is to be equals to ad1. ad1 means action in the direction of 1, or simple in the simple language you can consider that the applied moment. So here if you look towards the example, in this example at joint b no any applied moment is there. At joint b or at joint c no any applied moment is there, that's why in the both equation ad1 is equal to 0, ad2 equal to 0, that is at joint b and joint c applied moment is 0, that's why we are written equals to 0. Now come to the writing down the second equation. Now how to write the second equation? So here second equation is to be written by considering the second joint. So second joint is joint c, second joint is joint c. Okay, so what writing down this equation means, just consider joint c, whatever is written, whatever is the moment acting at joint c, write down that thing, means we will get this total equation. So at joint c we are getting here moment as 22.5, right, than 22.5. Next, at joint C we are getting this equation, the moment that is EI upon 2, and that is going clockwise, that is positive. So plus 0.5 EI, and this total diagram is multiplied by D1, that's why I multiplied by D1. Next, at joint C moment is only EI, moment is only EI, so EI again multiplied by total diagram multiplied by D2, that's why EI into D2, that is to be equals to applied moment. Applied at joint C there is no any applied moment, that's why that is to be equal to 0. So in this way you can write the equation even if we are not knowing how to write the stiffness coefficient, how to write this. If you are forgotten this equation, even though you can write these two equations. So ultimate goal is to write these two equations. By writing these two equations we can get these two unknowns. This is the ultimate goal, to get the unknown, that is D1 and D2. Now after getting D1 and D2, now again come to the main problem. So in the given problem, A and B are fixed and continuous support respectively. That's why there will exist a moment, there will exist a support moment, and C is a simple end support, that's why at joint C moment will be equal to 0. Now how to find the moment at joint A and at joint B? Now come to that part. So here I written this calculation required for MAB. So now come to the calculation of MAB. So to get moment at A, we are going to consider again these three diagrams. That is restrained structure, application of D1, application of D2. Just we have to consider these three diagrams. In that just consider the AB position. We are going to find MAB, that's why consider only this position. So this moment is going minus, that's why take this minus 16. This is going clockwise, so take it plus, and total this diagram is multiplied by D1. So minus 16 plus EI multiplied by D1, and here there is no any moment, that's why it will be 0. Same I have written over here, minus 16 plus EI into multiplied by D1. Now come to the writing how to find moment at BA. Now again come to the these three diagrams, restrained structure, D1 and D2. So we are going to find out MBA. That's why we have to consider only the moment which are written in a left side only. This is I drawn a line. This is a B joint. Only BA means just we have to consider left side moment. So this moment is going clockwise, that is plus 16. Just we have to consider left side moment, that means we have to consider only this one, BA. I am going to deal with only BA, so only this portion we have to consider. Plus 16 plus this 2 EI, and here there is no any moment. This 2 EI multiplied will be multiplied by D1. So same thing I have written over here, that is finding out MBA. Now how to find MBC? To find MBC, that is we are going to consider C joint. Sorry, we are going to find MBC means we have to consider the joint B, and just we have to consider right side of the B. Okay, but already we have found out the MBA. So of course, as the every joint will be in equilibrium, MBA will be equals to MBC. But still, for better understanding how to write this equation, given a write-up for BC also. So to find moment that is MBC. To find moment MBC, so BC means just we have to consider right side of the B joint, right side moment, that is minus 22.5. This is EI into multiplied by D1. This is EI by 2 multiplied by D2. Just only you have to consider right side of this fixed end. Now at last, of course, C joint is a simple support, end support. At that joint moment is 0. Now of course, just now next step is to draw BMD. To draw a BMD, just draw a straight line, that is a one baseline. Just show curves in this fashion. Next, this moment MAB we have got negative. MAB we have got negative means anti-clockwise. So here I have shown anti-clockwise moment. MBA we have got positive, means clockwise moment. BC we have got negative means anti-clockwise moment. And at C the moment is 0, that's why I have not shown any moment. Next, just observe this, all the curves. In all the curves, all the arrows are below a baseline. This arrow, this arrow, and this arrow, all the arrows are below baseline. That's why this at A and at B there will be a hogging type of bending moment. Or next, to draw a bending moment diagram, draw first of all a free BMD. So as AB portion is subject to UDL, the parabolic diagram will be there, and for point load this will be a triangle. This is the formula. We have got the W square by 8 and WAB by L for just simplified beam subjected to UDL and simplified beam subjected to point load. This is the maximum value of bending moment. Next, overlap. Of course, the free BMD will be positive because it will create a sagging type of bending moment. Now overlap on that a hogging type of bending moment, that is we have got hogging type of bending we have got from the support moment. So on the free BMD, on this free BMD, overlap a support BMD. Just we have overlapped the support BMD and we have got this final bending moment diagram.